Hello everyone and welcome to Memory Map for Motion in 2 Dimension. As you know, the goal of the memory map is to go through the chapter really quickly, so let's begin. We begin with the first idea of 2D motion, that is of motion in a plane. Now this idea comes from the fact that when you had motion in 1 dimension, you looked at motion in a straight line. When you are looking at motion in 2 dimensions, what you are looking at is a motion in a plane, that is motion on a surface. So under motion in a plane, let's look at the first condition, that is when an object is moving with uniform velocity. So we look at certain terms under this umbrella, that is when an object is moving with uniform velocity, we have certain terms, that is a displacement vector, which is r is equal to r2 minus r1. Now the displacement vector is nothing but the difference between the position vectors. So as you can see, these are vectors and therefore the difference between two vectors can also be written as the difference between their components, and therefore r2 minus r1 can also be written as x2 minus x1 I cap plus y2 minus y1 j cap. So this is a displacement vector. The next vector is the velocity vector, and you must know by now from motion in 1 dimension that velocity is the rate of change of displacement. So you can find velocity from displacement. We then have the equation of the object, that is the equation of the object in 2D, and here you will see that the equation is x is equal to x naught plus vxt and y is equal to y naught plus vyt. Finally, we have the equation of path, and here the equation is y minus y naught is equal to Vy by Vx, x minus x naught. I will discuss this in detail. Let's look at what these terms mean. First of all, let's look at what is a displacement vector. If you have the motion of a body in a plane, like this spider moving on the tiles of the floor, you will see that you can always choose certain coordinates. You can choose your coordinate system and give this spider or any object on a surface a certain position by mentioning the x and the y component. After some time, this object moves from its place to a different position, and then you can mark the second position of the object as x2, y2. Now it's very easy to see that if you have a coordinate system in place, you will find that the position vector of this object from the origin to this point will be r1, and the position vector of the object from the origin to this position would be r2, and here you have the displacement vector, that is r2 minus r1. So this is what we mean by the displacement vector, which I explained earlier. The next one is the velocity vector, which I said you will get by deriving displacement with respect to time, because velocity is nothing but rate of change of displacement. Next, we have the equation of the object, where x is equal to x naught plus vxt and y is equal to y naught plus vyt. So if you take a look at any one of these equations, I can rewrite them as x minus x naught is equal to vxt. And x minus x naught is nothing but the displacement in the x direction. So this is the final position of the object in the x direction, and this is the initial position of the object in the x direction. So I can write this as the displacement along the x direction, and therefore this equation is nothing but the displacement along the x direction is equal to velocity in the x direction multiplied by the time. Now does this formula remind you of something? In motion in 1 dimension also, if you wanted to find the displacement, you would multiply the velocity by time. Remember, this is true only for cases where you have uniform velocity. That is why there is no acceleration term. And as you can see that the equation in 2D is just like the equation in 1D. Here you have two separate equations for the x direction and the y direction. That is, displacement along the x direction is nothing but velocity in x direction multiplied by time. The same goes for the y direction. Displacement in the y direction is velocity along the y direction multiplied by time. So you can see that equations of motion in 1 dimension have counterparts of their equations in 2 dimension. Finally, you look at the equation of the path. If you take a look at this equation, you will recognize that this is the equation of a straight line. How do we know that? You compare the equation given with the equation of a straight line, then you will see that here y is nothing but the y minus y naught. Here m is nothing but vy by vx, as you can see there, and x minus x naught is nothing but the displacement along the x direction. So here you can see that this represents nothing but the equation of a line, and therefore I can say that the motion of an object in 2D is nothing but a straight line when it is moving with uniform velocity. So I can say that the equation of the path in 2D when it has uniform velocity is a straight line. So this was some terms related to motion in a plane when the object has uniform velocity. Now let's look at what happens when the object has some acceleration, that is, it is a uniformly accelerated object. So when we look at uniformly accelerated motion, let's look at the velocity time relation first. The velocity time relation says Vx is equal to ux plus axt and Vy is equal to uy plus ayt. Now if you look at these equations, you will know that these are just like the equations in one dimension. The first kinematical equation looks exactly like this. And therefore you can see that that is nothing but the kinematical equations only. But here we have written two equations, one for each direction. So when you went from one dimension to two dimension, how did the equation change for uniformly accelerated motion? Instead of one equation, you have two equations, one for each direction. The same thing happens for the displacement time relation. In the displacement time relation also, you have the equations which look like your kinematical equation in one dimension. So, you know the equation S is equal to ut plus half at square, where S is nothing but the displacement. And if you take this y here, that's the displacement along the y direction, and x is the displacement along the x direction. So you can see that those equations are just these equations but written separately for both the directions. So one for y-axis and one for x-axis. We then move on to projectile motion. By far this is the most important concept in this chapter. Most of the questions are asked based on projectile motion. Let's quickly look at projectile motion. First, let's clarify what is projectile motion. Projectile motion is the motion of an object only under the force of gravity. An object that is projected and moves only under the force of gravity. Now, under projectile motion, there are two types. The first one is projectile motion where you have an angular projection. And what do you mean by an angular projection? Angular projection means that you have projected something with a velocity at an angle to the x-axis. This is known as angular projection, where the velocity of the object which you have thrown or projected is at an angle with the x-axis. So this is known as angular projection. This is the first type of projectile motion under which we have certain terms. The first term is the equation of trajectory. Now you can see this is a fairly complicated equation which you will rarely need. If you remember the equations along the x and y direction separately, that is also most of the time sufficient to solve your sums. We also have time of flight t is equal to 2u sine theta by g, range r is equal to u square sine 2 theta by g, and maximum height, that is h is equal to u square sine square theta by 2g. Now of course I'm not going to show you how to derive these equations, but let's look at what these terms mean. If I kick a ball in the air, I know that it's going to perform projectile motion because it is moving only under the force of gravity. So this object here is performing projectile motion, this ball here is performing projectile motion, and now you can see that this is the initial velocity u with which this object was projected, and this velocity u was at an angle with the x-axis, and that's why I said this is an angular projection. Now this velocity can be resolved in two components, u cos theta, which is the velocity along the x direction, and u sin theta, which is the velocity along the y direction. Now this height, that is the maximum height of the object, that is height of the object at the highest point of motion, this height is known as the maximum height, and the formula is u square sine square theta by 2g, and this is the range, that is the horizontal distance from the point of projection to the point where it comes back on the ground. This is the horizontal range. So r is equal to u square sine 2 theta by g. Now be careful, most of the times people confuse this formula with this or vice versa. This has a square and is divided by 2. This has 2 on top and has no 2 in the denominator. So be careful. So this is the maximum height and this is the range. We also have time of flight, that is t is equal to 2u sine theta by g, and this formula is for the time taken for the object to come back to the ground, that is the time for the entire motion to get over. And finally you have the equation of trajectory here. Now the only thing to remember about the equation of trajectory qualitatively is that this is the equation of a parabola, and therefore projectile motion where there is an angular projection is nothing but a parabolic motion. So the object will always have a parabolic curve. We also look at the time of flight. Time of flight is nothing but the time taken by the object from the moment it is projected to the point where it comes back on the ground, given by this formula. And as I've already said, range is the horizontal distance from the point of projection till it comes back down. The horizontal distance is the range. And finally, maximum height is the maximum height from the point of projection which a projectile can reach. So these were the terms in angular projection. Let's also take a look at projectile motion where I have horizontal projection. What is horizontal projection? Horizontal projection means that now I have projected the object only with a horizontal velocity. Remember, before it was at an angle and therefore there were two components to the velocity, one along the y and one along the x. Now the object has only a component along the x direction at the point of projection. So this is known as horizontal projectile. Let's look at certain terms under the horizontal projectile concept. Here you have the equation of trajectory. As you can see, the equation is fairly simple in comparison to the equation of angular projection. That's obvious because now you have velocity only moving in one direction, at least in the beginning. Next we have the time of flight, again fairly simple. Finally we have the range, r is equal to u root 2h by g. Let's quickly take a look at an example for this. So for example, if a person shoots a bullet from a gun, so as you can see, the bullet will come out with a horizontal velocity. That is, it will have a velocity only in the x direction at the moment when the bullet is shot. And it will take a projectile path like this, and this is the path of the projectile. Now here, as you can see, the velocity initially is only horizontal, that is, it is only along the x direction. After some time, this object will move, come to a point pxy, some random point in its path that we have chosen. At this point, I can see that the velocity is no longer horizontal because it is moving like this. At this point, I can resolve the velocity into Vx and Vy, and this theta is the angle that the velocity of the object makes with the x-axis at any point in the motion. So quickly we can see that this is the range of the object, that is the horizontal distance again from the point of projection to the point where it reaches the ground again. This is the range of the projectile, the horizontal distance, r is equal to u root 2h by g. Finally, we also have two other formulae. One is the equation of the trajectory, y is equal to half gx square upon u square, and the time of flight t is equal to root 2h by g. So to recap, we have the equation of trajectory, y is equal to half gx square by u square. We have the time of flight, that is the time from the point of projection to when it comes back to the ground, t is equal to root 2h by g. And we have the range, horizontal distance from the point of projection to when it comes back down again, r is equal to u root 2h by g. So this completes projectile motion. Let's now move on to uniform circular motion. As you can see, the term uniform circular motion itself tells us that it's circular motion with a uniform speed. We have certain terms associated with UCM, that is time period, frequency, centripetal acceleration and centripetal force. Time period is given by t is equal to 2 pi r by v. Frequency is n is equal to v by 2 pi r. Centripetal acceleration is minus omega square r and centripetal force is minus mr omega square. Let me show you these terms with the help of an example. As you can see here, Professor Nipun is using a string and a stone, and he's whirling the stone or a ball in a horizontal circle. Now this is nothing but uniform circular motion. Now in this uniform circular motion, I'm going to show you what the terms mean. As you can see, this is the centripetal force, that is minus mr omega square. This is the magnitude of the centripetal force. It is directed towards the center of the horizontal circle. Let's look at the top view of this circle. This is how it looks. This is the center. You have the centripetal force acting inside. So this is nothing but the formula for the centripetal force. From here we can get the formula for acceleration, that is centripetal acceleration, because force is mass into acceleration. So you just drop the m and you get acceleration minus omega square r. Here you can see this is centripetal acceleration. You have n, that is the frequency of revolution. That is n is equal to v upon 2 pi r. That is the number of revolutions that the object will make per unit time. So that is v upon 2 pi r, where v is the speed and r is the radius of the circle. Finally, you have t, time period is equal to 2 pi r upon v, where r again is the radius of the circle and v is the speed. So these are the terms related to uniform circular motion. We then move on to non-uniform circular motion. Non-uniform circular motion basically means different types of motion. Like the first one is a curved unbanked road. So if you have a car that is taking a turn on an unbanked road means a road which is not raised as compared to the ground. So here you have an unbanked road, the car is taking a turn, and as you can see, forces acting in the horizontal direction on this car are the centripetal force mv square by r. Why is there a centripetal force? Because the car is taking a turn. So it's making a turn that is having a circular motion for that period of time, and therefore there's centripetal force towards the center of this turn. And therefore the condition for not skidding is that v should be less than or equal to root mu s rg, where mu s is the coefficient of static friction and r is the radius of the circle. So as you can see here, the car has no help in preventing it from skidding. All it has is the frictional force that will stop it from skidding. Okay, so here this is the condition for not skidding when you have an unbanked road. Let's look at what happens when the car is coming on a banked road. If the car is coming on a banked road means a road which is raised as compared to the floor. So you can see it's making a certain angle with the horizontal axis. That means this road is lifted high, and this is done on purpose. And why is this done on purpose? Because if you lift this road at an angle, then what happens is that the normal reaction is no longer straight. The normal reaction is at an angle. And what happens when the normal reaction is at an angle? There will be a component of this normal reaction along the horizontal axis. And this component will help you to prevent skidding in your car. So this extra component is now added to your horizontal direction forces, and this component helps to not skid. And therefore now the new condition for not skidding is not root mu s rg, but here the condition is root rg tan theta, where r is the radius of curvature and theta is the angle of banking, that is the angle between the elevated road and the horizontal direction. Finally, we take a look at bending. That is, we look at why sometimes if you look at bikers, they are bending when they are taking a turn. So why are bikers bending? They are doing this so that they can create extra centripetal acceleration to not skid when they take this turn. So again, you will see that you have the weight of the biker downwards, and the normal reaction is no longer again in the vertical direction but at an angle. And why is it at an angle? It's at an angle because the cyclist or the biker is bending, and they are purposely bending because now the normal reaction is at an angle, and because it's at an angle there is an extra component here which is now going to provide the centripetal force, that is mv square by r. So they no longer have to rely on the banking of the road, they no longer have to rely on someone else making the elevation. They just use their own normal reaction to help them go in a tight circle, that is to take a tight turn. So this r sine theta, r is nothing but the reaction of the ground, and r includes the normal reaction and the frictional force. So r sine theta component of the contact forces, this component is produced on purpose by the biker because he is bending, and therefore there is a component, and this component is providing the centripetal force. And because of this equation, we get the no skidding condition, that is the theta. The angle with which the biker should bend is tan inverse v square by rg, where v is the speed, r is the radius, and g is acceleration due to gravity. And from this formula, you can conclude that the angle through which the person should bend will be greater if the radius of the curve is smaller, r is in the denominator. So if r is small, the angle will be bigger, that is if the curve is sharper, and if the velocity of the vehicle is large. So the faster this biker is taking the turn, the more he'll have to bend to prevent himself from skidding. So these were the conditions on the banking and the unbanking, that is the non-uniform circular motion. Finally, we look at motion in a vertical circle. So we're looking at the motion in a vertical circle, and here you can see that this man runs and performs vertical circular motion in this setup. And this is actually a very difficult and extraordinary feat. But what we are trying to see here is what should the speed of the object that is trying to perform a vertical circular motion be at the different points. So let's take a look at what should the object speed be at the lowest point. Now at this lowest point A, the speed of the object should be greater than root 5 rg, where r is the radius of the circle and g of course is acceleration due to gravity. And if the object has this lowest speed, then only it can perform vertical circular motion. Similarly, at this point B, which is directly across the diameter in the x direction, here the object should have a speed greater than root 3 rg, where again r is the radius of the circle and g is acceleration due to gravity. And finally, to clear the top point of the circle, the object should have a speed of v is equal to root rg at the highest point of this circular motion. Only when it has these values can an object perform vertical circular motion, and therefore these are the values of the object speed at different points. Remember, here there is still centripetal force acting towards the center of this circle, which could be provided maybe by a tension in a string where you are turning the stone around in a vertical circle, or it could be a different force, but these are the values of the object speed. So this completes our analysis and overview of the chapter Motion in Two Dimension. This is the complete memory map. I hope you understood this series of horizontal projection. Thank you for watching. Please subscribe.